Hello, welcome to this lesson. In this video, you're going to learn about the phase relationship between current and voltage in a pure capacitor circuit. So we have this circuit here, we have an alternating voltage source and then a capacitor, which is the only element in this circuit here. So this voltage here, okay, will be the voltage from the alternating source, and then the C is the capacitance of the capacitor. Okay, so that C is the capacitance, and then it is normally measured in farads. And then what will happen is that when this voltage begins to pass through this circuit, the capacitor will be charged. Okay, what will happen is that at a point in time to be charged in one direction and then in the opposite at another time, because we have an alternating voltage source here. So this charge here is represented with Q. So that's the charge across the capacitor. Okay, so the voltage from the voltage source is given as V, which is equal to Vm sine omega t. Okay, so this is what you have. So what will happen is that there's going to be a voltage across this capacitor. Okay, we are going to represent this voltage with Vc. So because the only element in this circuit is the capacitor, the voltage on the capacitor will be equal to the voltage from the main source. So you are going to have V to be equal to Vc. Okay, this is what you are going to have. But the voltage across the capacitor will be equal to the charge over the capacitance. Okay, so you have Vc to be equal to the charge over the capacitance. Okay, so which means that before you can get voltage across the capacitor needs to be charged. That's what this means. Okay, so from here you can see that V equals Q over C. Okay, so this is what you have now. And then we know V to be equal to Vm sine omega t. So you have Vm sine omega t to be equal to Q over C. Okay, so from here I can make Q the subject. So I'm going to have the charge to be equal to C multiplying Vm sine omega t. Okay, so what you have here tells us that the charge will also be changing, okay, because of this expression here. That tells us that the charge will also be changing. So what will happen is that if you want to find the current across this capacitor, that will be I, okay, because the time rate of change of the charge, okay, on the capacitor. So you're going to have dq dt. So this will give us the current across the capacitor, which is the time rate of change of the charge on the capacitor. So this will give us I to be equal to the derivative of CVm sine omega t with respect to time. Okay, so let's differentiate this and see what you're going to get. When I find the derivative of this, I'm going to get CVm cosine of omega t times omega. Okay, this is what you are going to get after differentiating the charge with respect to time. So I'm going to write this as I equals omega CVm multiplying cosine of omega t. So this is what you are going to have. Okay, so this expression omega CVm is equal to the peak current Im. Okay, so you can write I as Im cosine of omega t. So this is what you will get for the current, but you see that from the voltage we're given sine omega t. Okay, so the voltage is V equals Vn sine omega t. And then for the current, you have cosine. So you can't compare the two to see the phase difference. So the best thing to do is to change this expression here to sine so that you can compare the two. So let's see what will happen. So I'm going to have I equals Im cosine of omega t. So I want to change this cosine of omega t to sine. Okay, so that would be, you can get cosine of omega t to be the same as sine of pi on 2 minus omega t. Okay, or sine of pi on 2 plus omega t. But you see that for the voltage, the omega t is positive. Okay, it is positive, so you have to use the second conversion so that it will match what we are doing. So let's go ahead. Okay, so we are going to have I to be equal to Im sine. See, so we have sine pi on 2 plus omega t. Okay, but I want it to match with the voltage expression, so I will write this as I equals Im sine omega t plus pi on 2. So this is what you have now. So you can now compare this to the voltage expression. So you have V equals Vm sine omega t. So from here you can see that the current, this is the voltage by pi on 2, which is the same as 90 degrees. So you will see that in this circuit, the current leads the voltage by pi on 2 or 90 degrees. That's what this means. Okay, so one thing I want us to look at is the capacitive reactance, okay, which is represented with XL. So let's look at what you are going to do about that also. Okay, so from this point, okay, let me circulate. Okay, so from this point here, okay, we are going to generate the formula for capacitive reactance. Okay, so we have omega c multiplying the peak voltage to be equal to the peak current. Okay, so what I'll do is that I'm going to divide both sides by the peak current. So I have divided by Im here, divided by Im. So this will cancel out this. So then we are going to have um, 1 equals omega c Vm over Im. Okay, so what I'll do is that I'll multiply both sides by 1 over omega c, that I can cancel out omega c from the right hand side. So I'm going to have 1 over omega c here. So this will cancel out this. Okay, so then you're going to have 1 over omega c to be equal to Vn over Im. Okay, and then this will actually be equal to the maximum capacitive reactance. Okay, so I'll make it as Xc, which is the maximum capacitive reactance. This is because we are using the peak voltage over the peak current. Okay, so this actually tells us that the capacitive reactance of a capacitor is given as Xc, which is equal to 1 over omega c. So this is what it means. Okay, where c is in farads. Okay, so in a situation whereby c is in farads in this case, then we are going to get the capacitive reactance Xc to be in ohms. Let's take note of this. So let's look at this diagram, which will actually tell us the phase relation between current and voltage in this circuit. So I have this figure here, and then from this figure we have this to be the voltage wave. Let me look at this. We have this wave to be the voltage wave, and then we have this one to be the current wave. So from this figure here, you can see that the current wave leads the voltage wave by pi on 2. Okay, so this tells us the phase ratio between voltage and current in a pure capacitor circuit. Thank you very much for watching this video. Please make sure you like the video and subscribe to the channel.